Assalamualaikum and hello everyone. My name is Nurul Shazwani binti Shahar with matrix number 2020820506. So in this video, I will present for chapter 2 topic the laws of logic. We have 12 laws in this topic. The first one is double negation law. When you see the negation is double, we can use this law to make it into natural P. Next, we have De Morgan's law, commutative law, associative law, distributive law, and idempotent law. The RDC, we have inverse law, identity law, domination law. We also have definition of implication and definition of biconditional. And the last one is we have absorption law. Now we will look some example for this topic. So this question asks you to show that the following expression is a tautology by using the laws of logic. First of all, try to identify which law that we can use from the expression. As we can see here, we can use absorption law for expression in the first bracket. After that, we can change the implies into or. This is definition of implication. Next, we can use De Morgan's law because we see there is negation symbol in front of the bracket. Then, we see there is double negation. So, we use double negation law to make it into natural P. After that, we combine the P using associative law. Next, when we see in bracket P or P, which is the same capital, we can make it into one P only. This is idempotent law. Then, we change in bracket negation ROR into contradiction using inverse law. And the last one is, we use domination law, which is P or contradiction into tautology. Since we got tautology there, so the expression is logically implies. Next, we have example 2. So this question asks you to simplify the following expression. We try to do for early bracket first, which is we change it using definition of biconditional. Then, we use commutative law followed by associative and absorption law. Lastly, we use definition of biconditional. Therefore, we got the answer. Last example for this topic. When we see this expression, try to change the implied first, using definition of implication followed by commutative law. Then, we eliminate P using associative law followed by absorption law. Next, we change the implies again using definition of implication. After that, we use De Morgan's law followed by associative and inverse law. Lastly, we got tautology by using domination law. Since this expression is a tautology, so it is logically implies. That's all for this topic.
Hi, my name is Natasha Nurfaiza binti Jumansa, number ID 2020482086. I will explain about argument and give 3 examples about this subtopic. So basically, an argument is a set of initial statements called premises, followed by conclusion. P1, P2 until Pn is a premises that called hypothesis, therefore Q. So Q is the conclusion. From this, we can also write down the hypothesis P1 and P2 and until Pn implies with Q, which is the conclusion. These are examples of argument in paragraph and in symbolic logic. If I read my text, then I understand my homework. I understand my homework, therefore I read my text. From this, we must find and label the premises with alphabet. So P is a label for I read my text and Q is a label for I understand my homework. From this label of premises, we can get the argument in symbolic logic. This argument has 3 sentences, which is 2 premises and 1 conclusion. For the first sentence, we have if-then, which is implies. So P implies Q. For the second sentence only Q, it is because we don't have any symbol. For the third sentence, also only P, which is the conclusion. P is a conclusion because before sentence P, we have therefore. Next, an argument is valid if and only if, in every case where all the premises are true, the conclusion is true. Otherwise, the argument is invalid. So, to find the validity of argument, we have 3 ways, which is truth table, laws of logic, and rules of inference, but more practical by using rules of inference. Next, we are using truth table to find the validity of this argument. The argument is in bracket S implies T and in bracket negation T implies with negation S. We let M for the argument. So in this argument, we have alphabet S and T. T is TFTF because 2 power of 0 we get 1, so T 1 times. S is TTFF because 2 power of 1 we get 2, so T 2 times. S implies T is TFTT because T implies T is T, T implies F is F. Negation T is FTFT because negation T is F and negation F is T. In bracket S implies T and in bracket negation T is FFFT because T and F is F, F and T is F, also T and T is T. Negation S is FFTT because negation T is F and negation F is T. M is TTTT because F implies F is T, F implies T is T, also T implies T is T. The only condition implies you get F by using T implies F. If all the premises are T, so we get tautology. And automatically symbol implies will change to logically implies. So the argument is valid. Next, we are using laws of logic to find the validity of this argument. The argument is in bracket P implies Q and in bracket P and Q implies with Q using definition of implication to change P implies Q to negation P or Q. P and Q change to Q and P by using commutative law. Combine Q with negation P or Q by using association law. From in bracket negation P or Q and Q, we get only Q using absorption law. Change in bracket Q and P implies Q to negation in bracket Q and P or Q by using definition of implication. Substitute the negation by using De Morgan's law. Combine negation Q with Q using association law. Negation Q or Q we get T naught using inverse law. T naught or negation P, we get T naught by using domination law. If the answer is T naught, it means tautology, so automatically symbol implies will change to logically implies, so the argument is valid. Next, we are using rules of inference to find the validity of this argument. The argument is in bracket R implies T and negation T, and in bracket P or Q implies in bracket R and S, then implies with negation P. Alright, firstly, we must do list all the premises, which is number 1, R implies T, number 2, negation T, number 3, in bracket P or Q implies in bracket R and S. Alright, number 4, from 1 and 2, we get negation R by using modus tollens. Number 5, from 4, we get negation R or negation S by using rule of disjunctive amplification. Number 6, from 5, we take out the negation by using De Morgan's law. Number 7, from 3 and 6, we get negation in bracket P or Q by using modus tollens. Number 8, from 7, we substitute the negation by using De Morgan's law. Number 9, from 8, we get negation P by using rule of conjunctive simplification. The answer is same with the conclusion, which is negation P. Automatically, symbol implies will change to logically implies, so the argument is valid.
Hi, my name is Nur Fatina Billah binti Heslahidi. My student ID 2020881344. So today I want to talk about quantifier. There is two types of quantifier. First, existential quantifiers, and second, universal quantifiers. In quantified segment, if we want to verify which quantifier that statement use, let's look at the keyword. So in existential quantifiers, the keyword is there exists, some, at least. And for universal quantifiers, the keyword is for all, every. Let's look at the existential quantifiers. First, let's look in specific domain. Look at the example. Some K-pop fans are obsessed with the idol, so our domain, K-pop fans. Meanwhile, our PX, X are obsessed with the idol. So look at the answer. Look at the next example. There is a student in class B has a car or a house, so our domain, X, student in class B. Meanwhile, our PX, X has a car, and our QX, X has a house. So look at the answer. Okay, it's still existential quantifiers but in general domain. Let's look at the example. It's the same quantified statement, but look at our domain, which is X, all fans. So we must add another one statement, which is QX, X is a K-pop fans. So look at the answer. For second example, it's still the same quantified statement, but look at our domain, X is all students. So we add another statement, which is RX, X is a student in class B. So look at the answer. Now, let's look at universal quantifiers in specific domain. Look at the example. Every Muslim in this world must cover their aurat. So our domain, X. Muslim in this world. Meanwhile, our statement PX, X must cover the aurat. So look at the answer. For second example, every girl in this room love handbag and shoes. So look at our domain. X girls in this room, our PX, X love handbags, and our QX, X love shoes. So look at the answer. Let's look at general domain 2. Look at the example. It's the same quantified statement, but our domain has changed, which is all Muslim. So we add another statement. QX, X is a Muslim in this world. So as you guys can see, the answer it's the same as existential quantifiers. But as you guys can see, in existential quantifiers, we use and. But in this universal quantifiers, we use implies. So remember that. Let's look at the next example. It's the same quantified statement, but our domain has changed too, which is X all girls. So we add another statement, RX, X is a girl in this room. So look at the answer. Now, move on to quantifiers and logical connective. E is to determine the true value. Look at the table beside me. In existential quantifiers, if you want the statement to be true, you must have at least one case is true. Meanwhile, if you want the statement to be false, all cases must be false. Look at the universal quantifiers. If you want the statement to be true, all cases must be true. And if you want the statement to be false, at least there is one case is false. It's different from existential quantifiers. As you guys can see, it's negate from the existential quantifiers. So please take note. And lastly, nested quantifiers. Nested quantifiers are quantifiers that occur within the scope of the other quantifiers. Let's look at the example. Our universe is a positive integer. So look at the question 1. There exists X for all Y. X is less than or equal to Y. So it's true when X is equal to 1. Why? Because 1 is less than or equal to 1. 1 is less than or equal to 2. 1 is less than or equal to 3. It's the same for all the positive integers, so this statement is true. Now look at the question 2. For all X, there exists Y. X is less than Y. So it false when X is equal to 1. Why? Because 1 is not less than 1. 2 is not less than 1 or 2 or anything, so it's false. In the first step, it's already false when X is equal to 1. So in universal quantifiers, it is difficult to this statement to be true. That's all from me. Thank you. Bye.
My name is Nuroni Izzati binti Zulkifli with matrix number 2020626028. We'll explain about the forward-backward method and also the construction method. The forward-backward method. To prove if A then B is true, we assume that A is true. Then we use this method to show that B is true. To make specific of A, we go through a forward process. To reach the conclusion that B is true, we use backward process. The backward process begin by asking the key question, how or when can I conclude that B is true? With no symbols or no notation. Next, give an abstract answer to the key question. Last, apply the abstract answer to specific situation to give a specific answer. After these 3 steps, you will obtain a new statement B1. If you can show B1 is true, then B is true. Repeat backward process until no proper key question is apparent or until no proper answer is available. The forward process begin with statement A that you assume true, derive from A to become A1 that you know to be true. Aim to link up last statement from backward process. This is some example of forward-backward method. For this example, A until A6 we call analysis of proof. For example number 1, first identify A and B. Use backward process. First abstract the key question. how can I show that a triangle is isosceles? Second, show that two sides of the triangles are equal. Third, show that x equals to y. The forward process. First, how can I show that two real numbers are equal? Second, show that the difference of that two real numbers is equal to 0. Third, show that x minus y equals to 0. And then we can do condensed proof. Condensed proof is an explanation from analysis of proof. For example number 2, apply same step as number 1 and write condensed proof. Next, the construction method. It is used when the conclusion involves an existential quantifier. Notation. The construction method can be used if conclusion B is in the form of there is an object with a certain property such as something happened. For example number 1 of the construction method, the answer should have analysis of proof and condensed proof. First, identify A and B, and last, show that A3 is equal to B1. For example number 2, we use same step as number 1. We need to provide analysis of proof and also the condensed proof.
Assalamualaikum and hi everyone, my name is Nur Azul binti Nur Kamal and my matrix number is 2020477736. I will present to you chapter 3, 2 method, which is choose method and specialization method. So when we need to use choose method? We need to use choose method when in B we have universal quantifier. Example 1. If set as x squared minus 4x minus 12 greater than or equal to 0 and t x less than or equal to negative 2 or x greater than or equal to 6, then S subset to t. Example 1. We need to identify what is A and B. A is hypotenuse and B is conclusion. B1 define subset for all x element to S and x element to t. A1 we have to use choose because of the word for all x. Let's say A element to S. B2 will change and follow A1. So A element to T. A2 will forward from A1. So we choose A element to S and we need to substitute A into S. A3, after that we use factorization to get the value of A and then we can get the interval. A4 we can choose any number between this interval to be test value and substitute into A3. So we can see the symbol is greater than or equal to 0. So for A5 we need to pick the interval that have positive sign. For A6 we can change into A less than or equal to negative 2 or A greater than or equal to 6. Means that for A7 A can be written into these inequalities so that it can be A element to T. From here we can see that A7 is same with B2, so they are logically equivalent and it is perfect. Example 2. If set as x squared minus 4x minus 12 less than or equal to 0 and set t negative 2 less than or equal to x less than or equal to 6, then t subset to S. We need to identify what is A and B. A is hypotenuse and B is conclusion. B1 we need to define B. So for all x element to T and x element to S. A1 we need to choose because of the word for all x. So B2 will change. A should be shown in S. A2 we need to forward from A1. Just now we choose A element T in A1. So we need to substitute A into T at A. A3 from A2 means that A greater than or equal to negative 2 and A less than or equal to 6. A4 from A3 we can bring it into left hand side. A5 because of the word and we can use multiplication. Means that positive times negative we will get negative value, which is less than or equal to 0. A6 expand A5, A7, A element to S. Because the equation of A6 is same like the equation of S, so it proves that A7 is logically equivalent with B2. Specialization method. What is the specialization method? Actually, this method is combination of choose method and specialization method. We need to specialize because in A we have universal quantifier, and we need to use choose method also in specialization method because in B we have universal quantifier. Example 1. If F subset to G and G subset to H, then F subset to H. We have to identify A and B. Start with B1. For all X element to F, so that X element to H. A1 we need to choose because of the word for all X. Let's say A element to F, B2 will change A element to H. A2 defined from A, F subset with G. So for all B element to F, B element to G. A3 we do the same thing like A2 for G subset H. In A we have universal quantifier, so we need to take out all the information and specialize. A4 specialize A1 and A2 because they have same properties, which is element to F. So we can swap A value into B value. So A5, A element to G. A6, when A element to G, A will be element to H. We can see that A6 is logically equivalent with B2, so it is proven. Example 2. If P is subset to Q and function R is greater than or equal to S on Q, then R is greater than or equal to S on P. We need to identify A and B. Take note, in function we must have domain. So B1 for all X element to P, then Rx is greater than or equal to Sx. A1 we need to choose because of the word for all X. Let's say A element to P. B2 substitute A into B1, so Ra is greater than or equal to Sa. A2 define R subset S. For all B element to P, B element to Q. A3 we can do the same thing like A2 for Rx is greater than or equal to Sx. Substitute C into X. A4 we can take all the information given and specialize. Specialize A1 and A2 because they have the same properties, which is element to P. So we can swap the A value into B value and we can get A5, A element to Q. So A6 means that Ra is greater than or equal to Sa. Finally, we can see that Ac is logically equivalent with B2, so it is proven.